We want to understand in chapter 1 the meaning of dimensions and units for any physical quantity. In physics, we are dealing with physical quantities like mass, force, energy. All these are physical quantities that could be classified into two main groups. The first group, we call it the fundamental or basic physical quantity. This means that its nature is independent on another physical quantity. And we have some of the physical quantities are called derived physical quantity, which means that their dimensions or their nature is dependent on another physical quantities. We classify physical quantities into fundamental or basic physical quantities, and they are summarized in table 1. They are 7 quantities only, as we will see in the next slide. They are independent on any other physical quantities. These physical quantities, to describe its nature, we described it was called dimensions. Dimensions are certain symbols that describe the nature of these quantities. And of course, we have to specify what system of units we will use. So we will examine together the dimension of these quantities, and we will use what is called SI system. The SI system is the Système International, the international system of units. This system uses the meter for the length, the kilogram for the mass, the second for the time. Let's see table number 1 and understand what is basic physical quantities. Table number 1 summarize the basic physical quantities. For example, if we say mass, the symbol of mass is m, but we agreed upon that its dimensions is written m capital like this. This is the dimensions of the mass. If you think about mass, its nature is independent on any other physical quantity. It stands alone. Its nature is basic or fundamental. That's why we say that mass is a basic physical quantity. And we will use the SI units as mentioned before, the kilogram. Its abbreviation is kg, small letters. The second basic physical quantity is the length. If you are dealing with length, the symbol is L or h, the height, or d, the diameter, or r, the radius, or the depth, or. All this stands for length. You can have any symbol for length according to your physical quantity you're talking about or according to the used reference. But when you are talking about the dimensions of the length, it is L capital. We used the letter L, but L capital. Again, length is independent on any other physical quantity. And we will use the SI units, as we mentioned before, meter for measuring any length required. The third fundamental physical quantity is time. Time, maybe its symbol is T, but when dealing with dimensions, we will write it T capital. This is the dimension of time. And the SI units is the second, and it's abbreviated as small. If you see these three physical quantities, they are called the basic physical quantities, and they are also mechanical. These are the three mechanical basic physical quantities that we are used in most of the mechanical equations, as we will explain in the next examples. The electric current is also a basic physical quantity. Its dimensions is I capital, and its unit is A, which stands for ampere. The absolute temperature, its dimension is theta. Theta is the symbol theta. Theta is a circle and you have a line in its center. K is the unit, which is Kelvin. For sure, when you are dealing with the absolute temperature, you are measuring it with Kelvin. Number 6 is the luminous intensity. The luminous intensity, its dimensions is O, and again O capital. And its unit is called candela, and we abbreviated CD in small letters. The seventh and last basic physical quantity is the quantity of matter. It is the mole. Its symbol is, or its dimensions is MOL, but the first letter is capital, and its unit is MOL, which stands for the word mole. As you see, we have mentioned the 7 physical quantities which are basic. Basic means that their nature cannot be described according to other physical quantities. Any other physical quantity except these 7 will be noted as derived physical quantities. I can derive the dimensions from the relation between these 7 basic quantities. Let's see how we can do it. In table 2, we try to take some examples of this. The first example we want to discuss is the speed. Table 2 is talking about derived physical quantities. They are derived from a relation that related them to the basic 7. Let's have an example. The first example is the speed. If we want to see the speed is related to distance and time, dx over dt. Simply, it's distance over time. I want to write the dimensions of the speed. So, first of all, I will put the speed between 2 square brackets. Using square brackets means I want to write the dimensions. So, from the relation, first of all, you write the relation. And then we want to put distance over time. Distance, its dimension is L. Time, its dimension is T. That's why the speed dimensions are L over T. We can write it L T to the power minus 1. After you write the dimensions of the velocity, you can write the SI units for the velocity. Instead of L, use meter. Instead of T, use second. And of course, T to the power minus 1, second minus 1. And this is the unit we are using for the speed meter per second. Another example, if we want to find the dimensions of the acceleration. The symbol of acceleration is a small. The relation of the acceleration with speed, it is dv over dt. Simply, it is speed over time. So, after finding the dimensions of speed, we can find the dimension of acceleration by simply, it is L t to the power minus 1, the dimensions of velocity or speed. I will divide it by the dimensions of time. So it will be L t minus 2. And then to find the SI units, you will put, instead of L, you will put meter. Instead of T, you will put seconds. So it's meter second minus 2, which is meter per second square. You have to note that The gravitational acceleration, its symbol is g, which we are using in our problems. G equals 9.8 meter per second square. This gravitational acceleration is a kind of acceleration, so it will have the same dimensions. So if you have any acceleration, either it's acceleration or gravitational acceleration, you will have the same dimensions. Why? Because they have the same nature. Another example, the force. What is the force? The force is related to other physical quantity by the equation F equals ma. So by definition, force equals mass multiplied by acceleration. Again, we will take the dimensions of acceleration from this part, L, T, minus 2. This is acceleration alone. And then we will multiply it with m for the dimension of mass, which makes the dimensions of force mlt minus 2. If you want to write the SI units, it will be, instead of m, kilograms, instead of L, meter, instead of T, second minus 2, T minus 2, it will be second minus 2. This is the Newton which we are used to use this unit for the force. But when we are asking for the SI units, we are asking for this form to write it in kilograms, meter, seconds, and so on. The second example, or the following example, is the work. What is the work? The work is F dx. It's force multiplied by displacement. Force multiplied by displacement. Okay, now we will take the dimensions of the force, these dimensions of the force. We will multiply it by the dimensions of the displacement. Displacement is simply, its dimension is L. So m L t minus 2 will be multiplied with L, m L squared t minus 2. Then again, you can write the SI units. We are used that the unit of work is joule. This is exactly what is kilogram meter square second minus 2. If we want to find the dimensions of the kinetic energy, we will put the relation of the kinetic energy. Kinetic energy means the energy gained by the body due to its velocity. Kinetic energy equals half mv squared. I want to get its dimensions, so I will get the dimensions of each part alone. Half is just a number, it's a numerical constant, has no dimensions, it has no physical nature. M, its dimension is m capital. V, its dimension is L t minus 2. And you will have squared because in the relation you have half mv squared. Abbreviate this, it will be ml squared t minus 2. What do you notice? It is the same dimensions as the dimensions of work, which means that work, energy, and all types of energy have the same dimensions and same units. That's why we can make only the dimensions of work and use it for kinetic energy, use it for potential energy, and any kind of energy, electrical energy, chemical energy, any kind of energy, because the nature of energy is the same, so they have the same dimensions. You can do this as an exercise, how to get the dimensions of potential energy from the relation mgh. We know that to calculate the potential energy, we can multiply the mass with g, the gravitational acceleration, with h, the height. You can do the same, and you will also have the same result, which is ml squared t minus 2. So if you know the dimensions of any of the energies or the work, it's okay, don't make it again. The next example is the power. Power is what we called energy per unit time. It is work dW by dt. Simply, it is energy divided by time. So I will take the dimensions of energy and divide it with the dimensions of time. You will find that power is m L squared T minus 3. And if you want to write the SI units, it's kilogram meter square second minus 3, which is the watt. We are used to deal with the watt. This is the unit of power, which is joule per second. So don't forget that power is energy or work. They are the same, energy or work divided by time, simply. But of course, the relation is dW over dt. The next example is how to find the dimensions of the electric charge from the electric current. Current is dq over dt, which is charge divided by time. This is the relation between current and charge. So if I want to get the charge, it is current multiplied by time. So the dimensions of the charge equal the dimensions of current multiplied by the dimensions of time. But don't forget that the current is a fundamental basic physical quantity. So I have a dimension of current. I multiply T will give the dimension of charge. Ampere second is my SI unit. Another example, the electric potential. The electric potential is work per unit charge. Take the dimension of work that is mentioned before and divide it by the dimensions of the electric charge, which we just found it in this part. Again, electric resistance is from Ohm's law V over I, and you can take the dimensions of V and divide it by the dimensions of current. Remember that the density of a material is mass per unit volume. Mass per unit volume. This is the density of the material. We use the symbol rho to express the density. If I want to get the dimension of the density, I will get the dimension of mass divided by the dimension of volume. What is the dimension of volume? Volume is multiplying three sides together. يبقى the dimension of volume is L cubed. For example, if I want to get the dimension of a cube, how do you get, if you want to get the volume of a cube, how you get it? You take this side, multiply by this side, multiply by this side, S squared cubed, S cubed. So the dimension of volume is L cubed. طب I want to ask you something. What's the dimensions of area? Area is just two sides multiplied together. So if you want the dimensions of area, it is only L squared, which means that two sides multiplied together. The density is M over V. M L minus 3. And of course, its SI units is kilogram per meter cube. The last example is the frequency. Frequency is the reciprocal of the periodic time. So dimensions of F is T minus 1 and its SI units is second minus 1, which is the hertz that we are using to um, to express the frequency. Another note that there is something called angular frequency. Its symbol is omega. The angular frequency has the same dimensions and units. As we mentioned before, this is frequency and this is frequency. That's why they have the same dimensions. After discussing table 1 and table 2, we are able to know that all physical quantities have dimensions, either if they are fundamental or derived. From this discussion, we can write together or we can discuss together the rules of the dimensional analysis theory. We want to know the rules of the dimensional analysis theory. The first rule that there are some quantities that are dimensionless. They have no dimensions and of course no units. For example, any trigonometric functions like sine, cosine, exponential, y, because sine the angle is the length of the opposite side divided by the length of the hypotenuse. Length divided length means no dimensions. So if you find any sine, any cosine, any exponential, these trigonometrical functions have no dimensions. Another example is the numerical constant. And we had this before when we were talking about the kinetic energy half mv squared. So we said the half has no dimensions because it has no nature, no physical nature, does not express any physical quantity. For example, if you have in the equation half negative 25 pi e, all these are examples of numerical constants which has no dimensions. And of course, no units. The third example is the angles. If we have an arc with an angle theta, theta in radians equals the length of the arc, L, divided by the radius r. L is the length of the arc, r is the radius of the arc. To get theta in radians, we just divide L over r. So again, this is length divided by length, which means no dimensions. We just say radians to differentiate degrees, then radians. So some quantities have no dimensions. Number two, when we want to add or subtract any physical quantities, they must have the same dimensions. For example, if you are adding length, you must add it to length, and the result will be length. It's nonsense to add length to time. What's the meaning of adding length to time? Nothing. So if you are adding or subtracting two terms, make sure that the two terms have the same dimensions and the result will have the same dimension. The third rule is, of course, the dimensions of the left hand side must be equal to the dimensions of the right hand side. If we are adding 3 meters plus 2 meters, the result is 5 meters. So the left hand side dimensions are the same as the right hand dimension. I cannot add 3 meters plus 2 meters and the result is second. No, it's meters. These three examples or these three rules are the rules of the dimensional analysis theory. What can I use this dimension analysis theory for? This theory could be used for several applications. Let's discuss together what are the applications we can use this theory in it. So this slide is talking about the applications of dimensional analysis theory. We have four main applications that we want to make some problems on it and to exercise on these applications. The first application is how to derive the dimensions and units of a derived physical quantity. This is exactly what we did in table 2. By knowing the relation which relates the physical quantity with the basic ones, we derived dimensions and units of the physical quantity. Number 2, I can use the dimensional analysis theory to check the validity of an equation. I want to check if this equation is correct or wrong, but from the dimensional point of view. So we will have example on this check. Number 3, to find the dimension and units of a physical constant. A physical constant in an equation have dimension and units. We want to get it. This is the application number 3. Application number 4, to derive the equation that relates a physical quantity. Using the dimensional analysis, we can derive an equation related physical quantities together. This is the most important application of dimensional analysis theory. How I can make this? We can write the equation as a physical quantity S proportional to a physical quantity X and Y and Z. But we don't know the power of proportionality. We know that S depends on X, Y, and Z, but we don't know to which power. We start our problem with a physical quantity proportional to X to the power alpha, Y to the power beta, Z to the power gamma. So S equals constant. This is a numerical constant. Instead of the proportional sign, I put equal constant, X to the power alpha, Y to the power beta, Z to the power gamma. And then I will write the dimensional equation. Instead of every physical quantity, I will write its dimensions. The last step is I will get alpha, beta, and gamma by equating the same powers, as we will see in the next example. Of course, K is a numerical constant. I can get it experimentally. Let's have examples for all these applications. As we mentioned before, finding the dimensions and unit of derived physical quantity is already done in table 2. The check the validity of an equation. This is an example for this. We have an equation x equals v naught t plus half at squared. X is a distance or displacement. V naught is an initial velocity. T is time. A is acceleration. And again, we have time squared. Of course, if you have this problem in the exam, we will write beside the problem that x is displacement. It will be clear in explaining the problem that x is a displacement, v is velocity, and so on. But of course, you know that these symbols are v for velocity, x for distance, but sometimes if I'm using v for volume, I have to mention v is for volume. Anyhow, in any problem in the exam, we will be very clear with the symbols. I want to check the validity of this equation. How to check it? Simply, if I checked the left-hand side dimensions and I checked the right-hand side dimensions, if I found they are the same, so this equation is dimensionally correct. Let's see. I will get the dimensions of the left-hand side. From the left-hand side, it's only one term, x. Dimensions of x is the dimensions of displacement, which is L. From the other side, I have two terms to be added together. So I will get the dimension of the right-hand side by adding the dimension of the first term and the dimension of the second term. For the first term, it's velocity multiplied by time. L over t is the dimensions of velocity, t is the dimensions of time, so all this will be L, or this will be L. Again, half at squared. Half has no dimension, so I put it in the dimension equation 1. A is acceleration. We did it before in table 2, L over t squared. T squared is time to the power 2 t squared. You can cancel this t squared with this t squared, so you will have again L. So this term is L, and the second one is also L. If you add L with L, the result is L. This is not an algebraic equation. This is a dimensional equation. I'm not adding x with x. I'm adding dimension L with dimension L. As we mentioned before, the result is L. So comparing the dimensions of the left-hand side and the dimensions of the right-hand side, you will find the same dimension. This is L and this is L. So I write that they have the same dimensions in the left and the same dimensions in the right. So this equation is dimensionally correct. Take care. I am just checking this equation from the dimensional point of view, but I don't know if it's physically correct or wrong because I don't know. I have to make an experiment to know if this is a physical equation correct or not. Maybe it's here not half, maybe it's doubled mass. Okay, was example number 1. Example number 2, I want to check the validity of this equation. This equation, t equals 2 pi root h rho over g. It's written in the example that t is the period of oscillations. So it is time. T is time. Period of oscillation, yani simply it's time. I don't have to understand the physics of the equation. I have to understand the mathematics and what does each symbol stands for. 2 pi, for sure 2 pi is a numerical constant. Root h. H, he's saying it's the height of a cylinder. Height of a cylinder, height of a building, I don't care. Height is simply height. It is the height of anything, but more or less it will be dimensions of length. And density, rho. Rho, we mentioned before that the symbol of the density is rho. So rho is the density. Density, rho. Divided by g. G is the gravitational acceleration. Without mentioning, we don't have to mention that g is the gravitational acceleration because it's well known that the symbol g small stands for the gravitational acceleration. Now we want to check if this equation is correct or not correct. Again, we are checking from the point of view of the dimensional analysis. It's just checking it mathematically. So we will get the dimensions of the left-hand side. From the left-hand side, it's the dimensions of time, so we put t capital. From the right-hand side, we will put the dimensions of 2 pi is 1. It's a numerical constant which has no dimensions, so it's just 1. Root h rho over g. H, its dimension is L. Rho, meter, or sorry, mass per unit volume. So it's m L minus 3. And g is acceleration, revise table 2, LT squared. Simplify this, you will have L minus 3, m t minus 2, all to the power half, because this root is a bracket to the power half, this square root. Okay, Have a look on the left-hand side dimensions, it's t. And have a look on the right-hand dimensions, it is something else. So they are not equal. So this equation is incorrect. It's not correct. This was example number 2. Now we will make another example, but on application 3. We said that the third application was to find the dimensions and units of a certain constant. This equation, we have force, the viscosity force, equals eta. Eta is the viscosity coefficient multiplied by these terms, AVH. As I mentioned before, they have to tell you that A is the area, H is the height, and V, you know that V stands for speed or velocity, speed. Okay, we know all these symbols and what does it mean physically. But we don't know viscosity coefficient, we don't know it. Here, he wants you to find the dimensions and units of this coefficient. Okay, to find it, put the viscosity coefficient in the left-hand side alone and all the other elements in the right-hand side. So eta equals F multiplied by H. H will go the other side. So F multiplied by H divided by AV. If this equation is correct, and he is saying it's correct, we can equate the dimensions of both sides. Remove F and put its dimensions. This is the dimensions of force, and this is the dimensions of H. This is the dimensions of the area, and this is the dimensions of V. Remember to check table 2 if you don't know any of these. Then simplify, you will find it ml minus 1, t minus 1. And if I want to get its SI units, instead of m, put kilograms, instead of L, put m, instead of t, put second, and same course. This is how to find dimensions and units of a physical constant in an equation. Another example, we have the gravitational force equals G, which is a universal gravitational constant, multiplied m1, m2 over r squared. We will discuss this later in the gravity unit, that if we have mass m1 and another mass m2, and the distance between them is r, so they have attraction gravitational force F, which is equal to a constant, a physical constant, m1, m2 over r squared. It's not important to understand the physical problem now. We are just discussing its mathematical view, not the physical problem. So it's required to get the dimensions and units of this physical constant. The physical constant G in the left-hand side and the other physical quantities in the other side. So r squared will be multiplied by F and m1, m2 will be divided. So G equals F r squared over m1, m2. Instead of every symbol, we will put its dimensions. Again, you will use the dimension of force. Here, r is a distance, so you'll use the dimension of distance. mm, because I have two masses, m1 and m2. Each one has a dimension of. Simplify and you get the dimensions of G capital, which is the universal gravitational constant. Again, if you want to get its SI units, use each unit instead of each dimension. These were two examples showing how to get dimensions and units of a physical quantity. The next example is somehow different using the trigonometric functions. In this example, they want me to find the dimensions and units of C1, C2, C3, C4. And the given equation is y equals C1 sine C2t minus 3 C3x plus C4. Of course, time is time. X and y are displacement. Displacement means just distance. So I want to find the dimensions of all these constants. If I get the dimensions of y from the left, it will be the dimensions of all this. It will be the dimensions of C and the dimensions of sine all the argument. Do you remember when I told you that sine anything has no dimensions? So sine any argument has no dimensions. So I put it all only one. Y equals C as dimensions. So the dimensions of C1 is the dimensions of Y, which is L, and the unit is M, because sine theta is dimensionless. Again, I will take the argument only. Argument only. Angles has no dimensions. So when dealing with sine theta, no dimensions. And theta alone is dimensionless. So the argument is dimensionless. I'm adding three terms. This is the first term, this is the second term, and this is the third term. This one is dimensionless, and this one is dimensionless, and the third one is dimensionless. Because we said before, adding terms together, they must have the same dimensions. So I want the result to be dimensionless. That's why we will take C2t dimensions equal 1, C3x dimensions equal 1, and C4 dimensions equal 1. From here, you find the dimensions of C2. From here, you find the dimensions of C3, and here directly the dimensions of C4. This example illustrates that when I find trigonometric function like sine all the argument has no dimensions and the argument has no dimensions. Now we finished three applications of the dimensional analysis theory. The fourth application was how to derive an equation from the dimensional analysis theory. We will take an example for this. Before we start, I will remind you what I said. If you have a physical quantity depending on another physical quantities, but you don't know the dependence, you don't know the power. Alpha, beta, gamma are unknowns. So you say that S is proportional to x to the power alpha, y to the power beta, z to the power gamma. Then you remove the proportional sign and you put equals constant x to the power alpha, y to the power beta, z to the power gamma. This constant is dimensionless and I can find it experimentally. Now we will use the dimensional analysis to find alpha, beta, gamma. How? By equating the powers of the same dimension. Let's see an example for this. In this example, f is the viscosity force, depends on r, radius of the sphere, v, the velocity, and eta is the viscosity coefficient. Here, it must be given its dimensions. You are not obliged to memorize its dimensions. And this is one of the givens. You can read the topic of this example in your sheet. Simply, F is a viscosity force. It's a force. For me, I'm just looking at it as a force. R is a radius, so it's only a length. V is a velocity, and eta given its dimensions. So we say F proportional to R to the power alpha, V to the power beta, E to the power gamma. It's required to find the relation between F and these three physical quantities, which means I have to find alpha, beta, and gamma. So we will remove the proportional sign and put equals constant r to the power alpha, v to the power beta, e to the power gamma. Then we will write the dimensional equation. Dimensional equation means that the dimensions of f equals the dimensions of all the right-hand side. Remove every quantity and put its dimensions instead. So remove f and put its dimensions. Remove r and put its dimensions. But remember that r to the power alpha, which is unknown power yet. Remove v and put instead its dimensions n to the power beta, which is unknown yet. Remove eta and put its dimensions with that, which I mentioned before that it will be given in this example. And of course, gamma is still unknown. Now we have ML and T in the left hand side, and we also have ML and T in the other hand side. For this equation to be dimensionally correct, we have to equate the powers. The powers of M and the power of L and the power of T must be equal in the left and in the right. So if you check the power of M, from the left, it's 1. And from the right, it's gamma. So gamma equals 1. If we check the power of L, or take T first, if we check the power of T, from the left, it's -2. But from the right, we have T to the power minus beta from this part, and we have T to the power minus gamma. So we add minus beta minus gamma. So equating the power of T in both sides, we have an equation relating beta and gamma. -2 equals negative beta negative gamma. We know that gamma equals 1, so beta equals 1 to satisfy this equation. Check the power of L. From the left, its power is 1. We don't have power, so it's 1. And from the right, L to the power alpha, L to the power beta, L to the power minus gamma. Add alpha, beta minus gamma. You have an equation relating alpha, beta, and gamma. You already got gamma equals 1, beta equals 1, so you can get alpha equals 1. Return to the equation. We didn't know before what are the powers alpha, beta, and gamma. Now we know that alpha equals 1, beta equals 1, and gamma equals 1. Rewrite the equation. So F equals K, it's a constant, dimensionless, R to the power 1, V to the power 1, E to the power 1. This is the equation that we are searching for. F equals constant, R, V. Let's check another example to how to find the relation between physical quantities using the dimensional analysis theory. In this example, it's required to find the relation between v, velocity, with e. Here it's Young's modulus. I don't know what's Young's modulus. I will know it in the next chapter. But because I don't know it here in chapter 1, so it's given that its units is Newton per meter square. What is Young's modulus? I don't know, and I don't want to know it now because I'm not studying the equation physically. I'm just studying it mathematically. So Young's modulus, it's given that its unit is Newton per meter square. Newton is the unit of force. So I can get the dimensions of E by knowing the relation. It is force divided by area. Area, because meter squared is a unit of area. Force over area from table 2, this is the dimensions of the force divided by the dimensions of the area. So dimensions of Young's modulus, which its symbol is E capital, is M, L minus 1, T minus 2. After simplifying this. So this is a relation between velocity, Young's modulus, and density of the medium. Density of the medium. Density, we know density is mass per unit. Of course, when you are checking the problem, this problem is also written in your sheet. Velocity of a mechanical waves. This is the velocity of a mechanical wave, which is passing through a medium. Depends on its Young's modulus and the density of the medium. I want to study this mathematically. So V proportional to E and rho. But I don't know the powers. The powers are unknown yet. Solution. V equals constant e to the power alpha rho to the power beta. Instead of writing this equation, we can write what is called dimensional equation. Instead of V, I write its dimensions. Instead of E, I write its dimensions, which I found it before. Instead of rho, I write its dimensions. Then the second step, by equating the power of similar dimensions, I have L, T, and M. L is to the power 1, T to the power negative 1, M is not clear here, which means that M is to the power 0. Anything to the power 0 equals 1. So, from the left, these are the powers of L, T, and M. And from the right, M and L and T have other powers. For L from this bracket to the power negative alpha, negative 1 multiplied by alpha is negative 1. Here, L negative beta. So equating these powers, I found an equation relating alpha and beta. As for T, here I find T to the power negative 2 alpha. As for M, I find M to the power alpha and M to the power beta. You have 3 equations to get alpha and beta. You need only 2. You can get alpha and beta easily. Easy. So after solving these equations, we found that alpha equals half and beta equals negative half. Instead of writing it like this, we can write V equals constant root E over rho. And for sure, this constant is a numerical constant which has no dimensions and could be easily found by experiment. Another example to find these equations is another example, it's written also in your sheet, the problem sheet. He's explaining that we have a fluid or a liquid moving in a tube. The length of the tube is L, and the V maximum is the maximum speed of the fluid. R capital is the radius of the tube, and he wants me to get the relation between all these quantities. So V maximum is speed proportional to pressure difference between the two sides of the tube, L of the tube, eta, we know eta, viscosity coefficient, and in this equation or in this problem, it's given its units, kilogram per meter second. We did it before. I can use the units to get the dimensions. So the dimensions of eta is, instead of kilogram, put m. Instead of m, put L. Instead of S, put T. M, L minus 1, T minus 1. This is the dimensions of eta, viscosity coefficient. Note that delta P is a pressure difference. Pressure difference means the dimensions of pressure. Why? Pressure difference is P2 minus P1. If I am subtracting two pressures, what is the result? The result is simply pressure. So difference in pressure is the same dimensions of pressure. Pressure is force per unit area. We can find the dimensions of force easily and divided by the dimensions of area to have m, L minus 1, T minus 2. Again, velocity is proportional to delta P to the power alpha, L to the power beta, eta to the power gamma, and also r squared. Now the power of r is known. R here is the radius of the tube. I can't have more than three unknowns, alpha, beta, and gamma, because I have three equations for the three powers. So the fourth power is given. If you read the problem, you will read that in the problem he is stating that this velocity is proportional to square of the radius. So I know the power of r. This is very important. Let's write the equation. So V maximum equals, instead of the proportional sign, we put equals constant, delta P to the power alpha, L to the power beta, eta to the power gamma, r squared. After writing the equation, we write the dimensional equation. What is the dimensional equation? It's the dimensions of every quantity. So this is the dimensions of V. We made it several times. This is the dimensions of P. Here you can revise it. L dimensions is L. Eta is given. And radius, its dimensions is L. But now I know the power. So in the dimensional equation, you have three unknowns only, alpha, beta, and gamma. How can I find alpha, beta, and gamma? By equating the powers of similar dimensions. Here I don't find m. We know that m to the power 0. Put the powers of L, m, and t from the left. L power equal 1. M power equal 0. T power equal negative 1. From the other side, you add the powers of every dimension. Let's see the power of L. L appears here in the first bracket to the power minus 1 gamma, so write minus gamma. L appears again to the power beta, add beta. L appeared again minus gamma. and L appeared for the fourth time, but with a known power 2. So add, don't forget this. As for M, from the left, it's 0. From the right, it is alpha plus gamma. Alpha plus gamma. As for T, from the left, it's negative 1. From the right, it's negative 2 gamma. And again, it appeared another time, negative gamma. You have 3 equations in 3 unknowns. You can get alpha, beta, and gamma. After solving this, alpha equals 1, gamma minus 1, beta minus 1. I write it like this: alpha equals 1, beta and gamma negative 1, so I put eta and L in the denominators, and r squared is given. This is the equation relating the velocity with the given physical quantities. This was the last example we want to discuss for the dimensional analysis. Thank you for listening.